Okay, now suppose we take that L, that piece of wire, and we rotate it about the x-axis. What it does, it creates an identical copy, sort of like this, and as this rotates, it occupies, remember, this is just like a line. It occupies just the surface. The inside of this is hollow. And the goal is really to figure out the area of this surface of revolution. So what we do, we cut this, the traditional, you know how this goes. And this is what we do. We take one of those pieces. Let's take this piece right here. If I take this piece, if I take that piece and I look at it, it's gonna look like this if I turn it. I'm really looking at an upper and a bit smaller the way this is, right? So if I look at what this is, isn't that right there? Oops, I cluttered that. Isn't that right there sort of like the radius? Wouldn't that be? So this is, let's say, the first piece. Wouldn't you say if that is x sub 1, x sub 2, x sub 3, wouldn't that be f of x sub 1, which is the radius? Remember what I want. I just want the area of the surface, the shell of this, right? The surrounding, not the inside. So actually this is not doing it justice. Let me pick a different color. Here we go. Let's go with this. This would be, I just want the area of the surface, nothing else. So this is hollow on this side and this side. Well, let's see how this plays. If I really look at this, that would be the area of the surface would be, well, it's going to be 2 pi r h, right? 2 pi r for the surrounding, the circumference of the circle, times the height. Kind of like saying the shell of this can. You'll say, well, okay, take this surrounding, which is 2 pi r, multiply it by the height. Well, what would that be? That would be 2 pi, and r in this case, for the first piece, I got it to be f of x sub 1. And do you see what the height is? Isn't the height really that distance? Isn't that delta S1? And if I take the second piece, if I look now at, let's say, what color should I use? Something that everybody could see. If I take this piece, well, wouldn't you say that's going to look again like one of those? And again, this is not straight. Here you could say the height because that's fixed. That's 90 degrees. Here it has a tilt. Do you see that? That tilt right there. Well, that's delta S2. This is the radius. Well, the radius now is, if that's x2, that's really f of x2 because that's that height. So for the second piece, it's going to be 2 pi f of x2 delta S. Well, delta S is the same in each of those, right? Since we're picking those, it's just going to vary depending on where x is. So if I really look at this, I could say the surface area is going to be 2 pi f of x sub 1 delta S for the first piece, plus 2 pi f of x2 times delta S. I'm so used to delta x, forgive me. Plus, and the last piece, 2 pi f of x sub n delta S. Oh boy. Old habits, hard to die. Surface area is going to be the series I equal 1 to n, roughly, of 2 pi f of x sub I delta S. And if I really want it to be equal, not approximate, I'll take the limit as n approaches infinity. The series I equal 1 to n of 2 pi f of x sub I delta S. And the surface would be, in this case, the integral from a to b of 2 pi, right? F of x sub I would be y ds. And this is by rotating y equal f of x about the x-axis. And it turns out S would equal the integral from some c to d of 2 pi times x ds if I rotate x equal g of y about the y-axis. The same idea, really. It works out the same way. And the key in this section is identical to what we did in the previous section, except what? ds is the key. That's where you start, except there's an x there and there's a y there. And if I start on this problem, it says set up an integral for the area of the surface generated by revolving the given curve about the indicated axis. So by seeing that it's about the x-axis, all what you have to remember is that s equal the integral of 2 pi y ds. The tough part turns out to be, do you leave the y in or not? And guess how do you decide that? You decide that by section 6.3. You start, remember, 2 pi is a constant. You could drag that up front. ds is, that's where you start. That's the key. When you look at ds, you glance at those. This is in terms of x. Well, isn't it easy to say that's 1 plus for ds? Take a derivative of that. Isn't that 1 over twice the square root of x squared? So if I want dx, can I leave a y right there and this is in terms of x? Well, definitely not. Instead of y, I should write what y equal. And that turns out to be the challenging part. What does y equal? Radical x. And of course, I'm going to integrate from 0 to 4. And that would be the setup. That's what they want us to do on the first set of problems. And there it is. Really basic and simple. If you understood the previous section, if you didn't, go back and make sure you review it. If I look at a number like 4, same deal. If I want to figure out what the area of the surface, I'll say surface area is the integral of 2 pi x ds. How do I decide that? Because you're rotating about the y-axis. Well, 2 pi is a constant. ds is the key. When I glance at this, I notice the limits are in terms of y, and this is y. Now, of course, I could, if I want, transfer the problem. I'll show you. But as is, wouldn't it be easy just to take a derivative? X prime is negative the sine of y. That means this is with respect to y. If this is with respect to y, can I leave an x there? Well, of course not. What does x equal? The cosine of y from y equals 0 to y equal 2 pi. I just want to demonstrate. You don't have to do this, but theoretically, you could do every problem both ways. You could say, you know what? I don't want to do it this way. You could have done that here too, right? You could say here, well, look, x equal y squared. And y varies between, if you put a 0 in there, isn't that a 0? If you put a 4 in there, isn't that a 2? And you could say s equal, or s equal the integral of 2 pi. You could say it's going to be the square root of 1 plus 2y squared dy. And now, since that's a delta y, I could leave this as y from 0 to 2. If you could work those two out, again, when would you want to do something like that? If you can't integrate for some reason, same deal here. I could say, you know what, forget this. Y equal the inverse cosine of x. I don't know why you want to do that, but let's say you might. And you could say x is between. If you put 0 in for y, cosine of 0 is 1. And if cosine of 2 pi is 1, oh boy, this integral is going to be 0. Nice. Even, yeah, that's going to be 0. Anyways. So in this case, you'll get a 0. But you could do theoretically every problem both ways if you like. That's not a problem. And it doesn't matter which way you set it up, any way you like. And if I look at the last problem, well, it says find the area. So in the beginning it says set up On the exam, most likely I'm going to ask for a setup more than anything on those. You know, remember, in an hour and 5 minutes, I could only ask as much. So, if I rotate this, oh, I forgot to mention. So, if I say in part A about x-axis, and if I say in part B about y-axis, well, let's see how this plays. If I take part A, and you're gonna notice something nice about this. If I take part A, I would say about the x-axis, s equal the integral of 2 pi y ds. That's gonna be twice pi the integral, and let's see. I'm gonna decide which way I'm gonna do this. This is gonna be 1 plus, well, it seems I'm gonna take x prime. X prime would be bring the power down, subtract 1 from the power. So 1/3, so that's y to the 1/2, right? Minus 1/2 y to the negative 1/2. We just did that in the previous section. That becomes a perfect squared. We're not gonna worry about that. I'm gonna do this from 1 to 3. Now, do you notice this is a delta y? What does that mean? I could leave this as y, which is the key. And if I look at rotated about the y-axis, s equal the integral of 2 pi x ds. Guess what? Students try to tie the x with the dx and the rotated about. None of that is true. I already got the work. That is 2 pi, the integral 1 to 3, the square root of 1 plus. I'm just copying. Literally, I just did delta s. I don't have to do it again. And it doesn't matter whether you rotate about the x or the y, right? It makes no difference as far as the s is concerned. So that's what I tried to get you to really grasp out of section 6.3. If you didn't get that, you should review it. You really already messed it up. So that is the square root of y to the 1/2 minus 1/2 y to the negative 1/2 squared dy. And since this is a delta y, I can't leave that as an x. Instead, what am I going to put in? Well, what does y equal? I notice that y equal, oh, it doesn't want to move. Okay, I'll say s equal 2 pi, the integral from 1 to 3, instead of x, I'm going to have to replace what x equal because that's a delta y. So you can't have, not in this class, you can't have a dy and an x in there. That's not allowed. Somebody told me to do this trick and they said it works really well. Hopefully they're right. So when things don't work your way, you gotta adjust and maybe shrink it a bit more. There we go. Okay, and that'll do the trick. Actually, there it is. And there's the homework.